Alright, welcome to chapter 12, AP Chem. We're talking about solutions this chapter. Hopefully a few of these equations are going to be pretty familiar from Gen Chem, but the way that we're using them is quite a bit more difficult than Gen Chem, unfortunately, but it is still something we can do. We'll just kind of take our time and work through it together. So here we go, chapter 12. You guys are familiar with the terms solution, solvent, solute, that kind of stuff. Solution, homogeneous mixture of two or more substances. The solute is what's present in a smaller amount. The solvent is present in a larger amount. So you're familiar with these things like salt dissolved in water. Salt is the solute, water is the solvent. Atmospheric air that we're breathing in, nitrogen would be the solvent, oxygen would be one of the solutes, that sort of stuff. So here are some examples of solutions. You can have solutions that are made of gases, dissolved in other gases, like air, the example I just gave you there. Salt and water, I gave you the example of a solid being dissolved in a liquid. To make a liquid, solid to a solid, we can make an alloy this way. So here's two solids making another solid, like brass is made of copper and zinc together. Liquids can be dissolved in other liquids, like alcohol and water. Gases can be dissolved in solids, like hydrogen gas and palladium. There's a lot of different solutions. So a saturated solution contains the most solute that you can dissolve at a given temperature. And an unsaturated solution contains less solute than the solvent has the capacity to dissolve. So you can sort of think of adding, maybe sugar into coffee. If we get that sugar into coffee, as much sugar as we can, before it starts to fall out of solution, we would have it as a saturated solution. If we just put a little bit of sugar in coffee and we could dissolve more, that'd be an unsaturated solution. So pretty easy stuff so far. Now, if we got that coffee super smoking boiling hot and we put a ton of sugar in there, it'd dissolve a lot more sugar if it's boiling hot. And we could get that thing super saturated, which is way more solute than ought to be in there. And as that coffee cools, of course, stuff's going to start to fall out of there. So here's an example of supersaturated solution. Sodium acetate crystals will form around a seed crystal if we get a supersaturated solution. And so here's a solution that's holding way more sodium acetate than it should be able to, and that sodium acetate is basically looking for a way out. So they take this little tiny amount of a crystal and drop it in. And when they drop that tiny crystal, it gives us a platform to grow the crystals that kind of want to get out of there. So here's the solid sodium acetate growing and growing and growing all around that seed crystal because it was in a super saturated solution. So a few types of interactions you can have in a solution process. We have the solvent interacting with the solvent. So this would be like, let's say we're doing sugar and water. This would be water interacting with water. The solute-solute interaction would be sugar interacting with sugar. And then we have the one that we focus most on, solvent to solute, the water interacting with the sugar. And that's what we're most worried about. So a little molecular view of this. Step 1, our solvent spreading out. Step 2, our solute spreading out. Step 3, forming a solution out of our solvent and our solute. So you can say the delta H, or the enthalpy change of the solution, is equal to the enthalpy change of our solvent plus the enthalpy change of our solute. If there's another solute, the enthalpy change here of the solvent and solute mixing together. That's step 3. So like dissolves like is kind of the rule of thumb for dissolving things in a solution. Polar dissolves polar, but polar won't dissolve non-polar, kind of like the whole oil and water don't mix thing. So two substances with similar intermolecular forces are likely to be soluble in each other. So, the reason we can get sodium chloride dissolved in water is, well, water's polar, and sodium chloride's polar. They have positive and negative ends, so it works out pretty well. Non-polar molecules are soluble in non-polar solvents. Can't really dissolve like something non-polar like hexane in water, but we could dissolve hexane in like perhaps olive oil or benzene or pentane or some other non-polar liquid. So here they give the example of carbon tetrachloride, non-polar, dissolving in C6H6, which should be benzene. So a non-polar dissolving in a non-polar. Polar molecules are soluble in polar solvents. So here we have C2H5OH, so that's ethyl alcohol, ethanol, dissolved in water. And ionic compounds are more soluble in polar solvents, which kind of makes sense because, polar is the whole idea of separation of charge, unequal electron distribution, and ionic compounds tend to have, that positively charged ion and the negatively charged ion, and the anion's a little more electron greedy, so they get a separation of electrons too. Kind of makes sense. So, concentration of a solution. Here's where we start to bring the math into this chapter, and then we don't really look back after that. The amount of solute present in a given quantity of solvent or solution. We got to have terms like this. You might know like percent, maybe like vinegar is 4% acetic acid, or this gasoline I'm putting in my car contains up to 10% ethanol. That's one way to do it. But in science, we tend to use either a percent by mass or molality or molarity. So the first one's percent by mass. That's kind of the example I had given you, the 10% ethanol is 10 grams of ethanol in 10 grams of ethanol plus 90 grams of gasoline gives me my 10% ethanol. That's pretty easy way to figure that out. So mass of the solute divided by the mass of your solution times 100 gives you your percent by mass. Mole fraction is another one. This is one you might remember from, what did we do this in? Gas laws or something like that? X sub I remember doing that. So there's mole fraction, which was the moles of what we're interested in divided by the moles of everything in the solution. And we're going to use mole fraction later this chapter, so do refresh yourself on how to do that. Now here's one I hope you remember from Gen Chem, molarity. I don't even know if I gave you the equation for this. I think you had to memorize. Molarity is moles per liter. It was real easy to do. So molarity, the moles of the solute, what we're interested in, divided by the liters of solution. So the whole solution. And then there's molality, which is a little trickier. Moles of solute divided by mass of the solvent in kilograms. So not solution down here. Mass of the solvent, so kilograms of water, or kilograms of benzene, something like that. So we're going to work a lot with these. A lot. So, because we're in AP Chemistry, we're a little bit past that idea of you have this many moles and this many liters. What's the molarity? The real easy stuff that we really enjoyed doing. Now we're in something a little trickier. What's molality? That's little m of a 5.86 molar ethanol solution whose density is 0.927 grams per milliliter. So to solve this problem, we've got to get moles of ethanol divided by kilograms solvent. So here's how we're going to figure this out. This is our goal. Moles of our solute divided by mass of our solvent. And we already have molarity, which means we've got 5.86 moles of ethanol in 1 liter of solution. So we're going to start with an assumption. It makes it a little tricky when you start with assumptions, but we're going to assume there's 1 liter of solution. And for pretty much all problems in your book, start there too. Let's say we have a liter, because we have to start somewhere. So if we have a liter, then we have 5.86 moles, because molarity equals moles per liter. So if I have 1 liter and I'm 5.86 molar, then I have 5.86 moles of ethanol. So that's not too bad. We got 5.86 moles of ethanol. So that's going to give us 270 grams, because ethanol's C2H5O and H, and if you add all those up, you'll get their grams per mole. So just like we've done earlier in the year, you add up grams per mole, moles cancels out, and you're left with grams. So 270 grams. Now, if we need to get to a liter, then we can say we have 270 grams of ethanol, then we have 927 grams of solution. And we know that because if we have a liter of solution total, that's equal to 1,000 milliliters. And our density in this problem is given to us as 0.927 grams per milliliter. So we say, okay, if we got 1,000 milliliters is our assumption, times 0.927, then we're at 927 grams of solution. Now it's really important because if we can figure out the grams of our solution using our density and the grams of our ethanol using molarity, then if you subtract the solute from the solution, you get the mass of the solvent. And that's what we need to find. And so that's exactly what we do. We say, if we want to know how much the solvent weighs, then we take our whole solution minus our solute, and we get 657 grams. Now, this asks for kilograms for molality, so we just say there's 1,000 grams in a kilogram, divide by 1,000, move that decimal place over, 0.657 kilograms is our denominator. Now all we need is the moles of the solute, and that's very easy because given the assumption that we started with of 1 liter, we know that it's 5.86. So 5.86 moles of ethanol are solute divided by what we calculated to be 0.657 kilograms of the solvent gives us 8.29 molal, hard word to say, solution. So a little tricky, but the good news and the bad news is we're going to do a lot of these. So after you've done 9 or 10, they won't be so tricky anymore. Let's look at temperature and solubility. I kind of spoiled this for you earlier when I said if we can get that coffee really boiling hot, we can get a lot more sugar in that coffee. So it's kind of a spoiler alert for you, sorry. But if we look at how much solid we can dissolve in a liquid at a certain temperature, you can see that there are a couple exceptions. Like, what's this one? Looks like sodium sulfate and some cesium sulfate. But the general trend is if you increase the temperature, you increase the amount of solute that you can dissolve. Sometimes it's only a little bit of an increase, but other times, like with potassium nitrate, I mean, that increase is insane. Look at that. So if you were to kind of group all this data together and say, do a best fit line, it'd be a little weird, but it'd be something kind of like this, give or take. The trend is as you get hotter, you can dissolve more of solute rather. Here's salt was the example I gave you, and a lot of these are salts. They're just not salts we readily go out and purchase. This is the salt that, goes on French fries and stuff. So there's that line. Increases with increasing temperature. So there we have it. And then there's our two examples where that's not the case. All right. So fractional crystallization. It's the separation of a mixture of substances into pure components on the basis of differing solubilities. And so here is the solubility chart for a couple different things. Sodium chloride and potassium nitrate. And their solubilities are really very different. And so if we had 90 grams of potassium nitrate and we had 10 grams of sodium chloride, here they give us the word contaminated, so we're believing that we kind of want to get that sodium chloride out of there. The way we could do it is with fractional crystallization. If we dissolve the sample in 100 milliliters of water at 60 degrees Celsius, right here, and we cool it to 0 degrees Celsius over here, then what's going to happen is that salt is probably going to stay in solution, and 78 grams of potassium nitrate is going to precipitate. And so as we move this way with the temperature, this guy's sodium chloride's pretty much still going to be soluble here, but this red line for potassium nitrate really tanks down here when we start to get cold. So as we get cold, it's kind of like that potassium nitrate freezes and drops out of the solution. It's kind of the way you can think of that. So oxygen gas solubility and temperature. Here we're going to see something that's a little bit different, because now we're dissolving a gas in a liquid. And when you dissolve a gas in a liquid, it's sort of the opposite. If we get water very hot, it doesn't hold much oxygen gas. But if we get water very cold, it holds a lot of oxygen gas. And that's why fish species that we have here in Rapid Creek is really cold all the time, and a lot of the Black Hills streams are. And that's why we can support the fish species we can, like brown trout and rainbow trout. They wouldn't do real well if you took them to some warm water, stock dam out in the prairie and dumped them in there. They'd turn belly up. But you keep them in that frigid cold water, Rapid Creek, and they do pretty well there because it's really oxygen rich. And a couple other reasons too, but because it's oxygen rich helps. So solubility usually decreases with the increasing temperature. So that's for gases. If you want your pop to not go flat, don't let your pop heat up. Put that thing in the fridge, put it in the freezer, do something, because if that pop gets hot, backpack or your hand or whatever, that CO2 is going to leave pretty quick, just like oxygen would. So pressure and solubility of gases. Here's the kind of a pretty logical thing, but the solubility of a gas in a liquid is proportional to the pressure of the gas over the solution. So basically, if we put more pressure on a gas, more of the gas molecules will move into the liquid. Sort of makes sense. It's called Henry's law. Here's the formula. C equals K times P. C is the concentration in molarity. P is the pressure of the gas. And K is a constant for each gas. And that constant is in moles per liter atmosphere. That depends only on the temperature. So here's the example of a glass container with a liquid, and there's some dissolved gas in the liquid, and there's gas above the liquid. And then at a very low pressure, there's a pretty low concentration of dissolved gas in the liquid. Now, if we increase the pressure, we get a really high pressure in there, then we're going to have a higher concentration of dissolved gas in the liquid. So this is the last slide we're going to do for today. This is the example of a gas moving out of solution and some pretty awful results. They called it the Killer Lake, Lake Nyos in West Africa. And basically the lake gets this weird layering in it because of the rocks that make up the foundation of the lake. They release a lot of carbon dioxide, and that carbon dioxide kind of sits in this dense water at the bottom and is not able to make it out of the lake. And so it sort of just builds up. And in 1986, something happened in that lake. It might have been an earthquake or a landslide or strong winds. But basically, the lake sort of bubbled out or belched out a giant cloud of carbon dioxide. Carbon dioxide is heavier than air. And so CO2, which you can't smell, you can't see, you can't taste, filled the area near this lake, and that cloud traveled down a valley. And as it traveled down that valley, it killed wild animals, it killed livestock, killed 1,700 people, and nobody knew it was happening. Everybody asphyxiated. So kind of wild. Now the picture they've got for you here is it's basically a big water pump, because that lake is still producing a bunch of carbon dioxide. So now their idea is if we can pump water up from the bottom of the lake, fire it up into the air, that water will dissolve the CO2 out into the air slowly and not become this kind of creepy time bomb of invisible death that it's proved itself to be. So on that cheery note, that's where we're going to end for today. So thank you.